All right, so last lecture that I did on Monday, I said that we would be talking about the Hardy-Weinberg equilibrium, and that's what this entire lecture is going to be on. And I also will have you do a Bozeman video in the middle of this, so just be prepared for that. It's like 11 minutes, but it shows you exactly how to do the equations. So we'll just get started. So the Hardy-Weinberg equilibrium is a theoretical scenario that says this is what would happen. My dog, sorry. This is what would happen if no evolution occurred at all. So if we had no mutations, no etc., then we wouldn't have any change in allele frequencies, and there would be no natural selection and no evolution. So obviously that doesn't really happen in nature, so it is theoretical. But it's a model used to assess whether natural selection or other factors are causing evolution at a particular locus. And remember, locus means the location on a chromosome where specific genes and alleles are. Okay, so it determines what the genetic makeup of the population would be if it were not evolving. And this is then compared to the actual data in the population. So if there are no differences, then the population is not evolving. So if you look at this and you think that it sounds familiar, if we're comparing the observed with the theoretical, that would be chi-square, remember? So we will be using chi-square for this, but not the whole time. So if there are differences, then the population may be evolving. Doesn't mean it is evolving per se, but it may be evolving if there are differences in the genetic makeup and the allele frequencies. Okay, so the Hardy-Weinberg principle states that the frequencies of alleles and genotypes in a population will remain constant from generation to generation, provided that only Mendelian segregation, so the law of segregation, and recombination, which happens during crossing over and meiosis of alleles, are at work. So only segregation and recombination during meiosis are happening. There's no other outside factors that would cause evolution. So remember that this is, I'll get my face out of the way, a hypothetical situation where no evolution would take place. In real populations, the allele and genotype frequencies do change over time. So this is not a real situation or scenario because it just doesn't happen in nature. Okay. Okay, so there are 5 conditions that have to be met in order for Hardy-Weinberg equilibrium to be in place. So for no evolution to happen in a population, there has to be no mutations. There has to be random mating, so there's no sexual selection. It's just the ladies pick whoever, I don't know, like the first person that knocks on their door. There's also no natural selection, so that also means that there's no adaptations, because if there were adaptations or beneficial alleles over others, then there would be natural selection. So there's no natural selection. It has to also be a really large population size because small populations are affected by little things more so than large populations. If 10 of us, I don't know, if we're going to use coronavirus, if 10 of us all get the coronavirus and we're all for some reason vulnerable to it, then we'll be affected more so than a large population that most of them won't get it. I don't know why, just bear with me. There's also no gene flow, so there's no migration, because if there were migration, then populations could migrate to other populations, and then there would be a flow of genes and alleles. So there's no gene flow that happens, which also means no migration between populations. Okay, so if any of these conditions are not met, then microevolution occurs. Again, that's just evolution at a smaller level. So mutation would happen, gene flow, genetic drift, natural selection, and non-random mating. all cause microevolution. So it wouldn't be in Hardy-Weinberg equilibrium in that case. So you can't do this because obviously with a partner because you guys are online right now. But it says discuss with a partner or just discuss with yourself. You can talk to yourself, that's fine. How each of the 5 Hardy-Weinberg conditions, if not met, can lead to evolution. So I'm going to go back to here, and I kind of talked about these with you just now, but mutations, obviously, if you want to pause it for a second and think about it, that's fine, and then I'll go over them. But okay, so mutations obviously are going to cause alleles to be different, and if they're different, then one will be either beneficial over the other or not beneficial over the other, and then we have natural selection. So that would cause natural selection, which is the basis of evolution. So number 3 is knocked out, but if there's no random mating, for example, sexual selection, that's still a form of kind of a form of natural selection, but it's a form of evolution because where populations are selecting for specific traits in the males. So then evolution would happen and we would not be in Hardy-Weinberg equilibrium anymore. And then I just talked about the population size and gene flow. Okay, so there are 2 formulas. We're going to do a little bit of math here. Bear with me. But there's 2 formulas for Hardy-Weinberg equilibrium, the first of which is pretty easy. It's just P plus Q is equal to 1. P, and we'll talk about what P means. So P is the frequency of the dominant allele in a population. A good way of thinking of this, and it's kind of like a weird way, but how I learned it is dogs pee to assert their dominance. So just remember that P equals dominant. So we're talking about the dominant allele in the population. Speaking of dogs, mine is right behind me. Hey, come here. Say hi. Anyways, okay, so dogs pee to assert their dominance. So P is equal to the dominant allele in the population, the frequency of the dominant allele in a population. And then Q, as you can probably guess, is the frequency of the recessive allele. I don't have like a funny like saying to remember that. Just remember that P is dominant, and then you can do process of elimination and know that Q is a recessive allele in a population. We go over here. This is a more complicated one, but I swear it's pretty easy once you get a hang of it. So we have P squared plus 2PQ plus Q squared is equal to 1. So P squared is a percentage of the homozygous dominant individuals. Because they're homozygous dominant, it's just dominant times dominant, so we have P squared. And then we have the percentage of the heterozygous individuals because it's 2 times, and then they have a recessive and a dominant and a recessive allele. And then we have the percentage of the homozygous recessive individuals because the alleles are 2 homozygous, so you just times them by each other. And then that is equal to 1. Okay? I swear it'll make sense in a little bit. Okay, so first thing is you're told that 20% of a population is homozygous recessive, and it asks what variable is that referring to in the Hardy-Weinberg equation. So which letter or variable is the homozygous recessive referring to? The percentage of homozygous recessive. So it's Q squared. So remember, Q is recessive, and then Q squared is homozygous recessive because it's 2 Qs. And then you're told that the frequency of a dominant allele in a population is 75%. What variable is that referring to in the Hardy-Weinberg equation? So the frequency of a dominant allele in a population, so we're not talking about percentage, or like we're not talking about we're talking about percentage, but the frequency of a dominant allele in a population. Just the dominant allele. And that's P. So dogs pee to assert their dominance. P is equal to the dominant allele. Okay. Okay, so which formula you start with depends on the information you're given. Just like in math, you have all of these formulas, or physics, or whatever you want to talk about. Chemistry is a good one. But you are using the formulas that you know in order to solve a specific problem. So you'll only have what's given to you, and then you'll have the formulas, and you'll figure out which one works better for what I'm trying to find out and for what I already know about the equation. So if a problem gives allele frequencies, then it's referring to P and Q. So the dominant allele being P, remember, and then the Q being the recessive allele. So if it gives information about individual organisms or populations, then it's referring to the P squared, the 2PQ, and the Q2, or Q squared, sorry. Okay, so if it gives allele frequencies, then it's talking about P and Q. If it gives information about individual organisms or populations, then it's referring to the P squared, 2PQ, and the Q squared. So most of the time you'll use both formulas in order to complete the problem, just like you would do in any other class that has specific formulas that you use. And then usually you're given Q, and then you'll need to find P. Again, sorry, my face is in the way. But you will also have see the problems where that's not the case. So usually you're given Q, and then you'll need to find P. Okay. Y'all, my dog is going swimming right now. Okay, so a few tips for solving these equations or these problems. Always write down both of the equations that you know for Hardy-Weinberg equilibrium, just so it'll give you a good idea of what you know and then what you need to know or need to figure out via the equations. So you're going to identify the information given. Is it for alleles or for populations? And then regardless of what the problem asks, you're going to solve for both P and Q first, just because that'll allow you to answer any of the questions that it gives or that it presents to you. And then you'll use the calculator to do the square and square root functions. The most common mistake students make is assuming that they know the answer and just making very simple math mistakes. So as long as you do all of these, you will be golden. And then you're obviously going to double check your work, because if you're in a rush and you're just trying to do it quickly, usually you'll make a mistake that's very small and very fixable, as long as you check your work. Okay, so this is the video I was talking about. I'm gonna pause. You're gonna pause the video. I can't pause it for you. And you're going to go to this YouTube link. I don't think that you can watch it through here, or I don't think that I can play it through here. So you're just gonna go to this link. It's gonna be in the comments for this lecture. So just pause this and then click on the video link, and then you'll go through that by yourself. Okay. And then we'll do some practice problems. So pause me and come back for the rest of the lecture. Okay, so the practice problem number 1 for us. I know you just did a few with Mr. Anderson, good old Bozeman science. Okay, but so for number 1, it says you have sampled a population and found that 36% are homozygous recessive, meaning little a. And then it's asking you what's the frequency of the dominant A and the recessive A alleles. So we're going to write down our equation. So P plus Q is equal to 1, and then P squared plus 2PQ plus Q squared is equal to 1 as well. So we're given, well, I'll give you guys a second to do this. Feel free to pause it if you want. But I'm just going to go through these. So you're given that the Q squared, meaning the homozygous recessive, is 36%. Make sure that you put that in a decimal point, or in decimal form. So it's going to be 0.36. Does that make sense? Just like if it were 20%, it would be 0.2. Okay, so you're given that q squared is equal to 0.36, and you're going to solve for p and q first regardless. So do that real quick. So you should have that q, if we square root q squared, then it's just going to be q. So we know that q is going to be 0.6, right? And then p plus q is equal to 1. So we know that p plus 0.6 is equal to 1. So because we know that, then we know that p is equal to 1 minus 0.6, which is equal to 0.4. Okay? So now we know what q is, we know what p is, everything else is going to be super easy. All right, so the frequency of the A allele is 40% because we know that P is the dominant allele, and we got 0.4, which is 40%. So the frequency of the little A allele is 60%, and that's exactly what the question asks, the frequency of each of those. So it's 40% for the dominant allele, and then 60% for the recessive allele. Pretty easy, right? There will be harder ones, but this one is a good, neat, easy one. Okay, so the next one says 10% of a population of mice are albino. Albinism is recessive to tan coloring. What is the frequency of homozygous dominant and heterozygous individuals in the population? So right off the bat, we're being asked about a specific population. So we know kind of what we're going to need to be using. But again, I just want you to write it down. So both of the equations are here. So we have p plus q equals 1, p squared plus 2pq plus q squared is equal to 1. Again, we're given, again, that q squared, which is the population of homozygous recessive, because it's a recessive, they're albino, which means that they have an allele that, or two alleles that are recessive. So they're homozygous recessive. So we know that q squared is equal to 0.1, which is the 10%. And we're solving for the 2pq and the p squared. So the number that are heterozygous and then the number that are homozygous and dominant, right? So I'm going to give you guys a second, pause this if you want to like practice on your own, and then we'll go through it. All right, so again, since we're giving q squared, we can easily, we're solving for p and q first. Don't try to solve for 2pq or q squared first, because we need p and q. It'll make it much easier. So again, q squared, if we just square root it, is 0.32. And then p plus q is equal to 1. So we know that p plus 0.32 is going to be 68. So it's 0.68 for p, or 68%. And then we can just square that, easily get 0.46. So since we know that the p is going to be dominant, then we know that p squared is homozygous dominant. So that's one of the questions. So it's 0.46 or 46%. And then we can easily just fill that in with a p and q because we know exactly what those are. So 2pq is just 2 times 0.68 times 0.32, and we get 0.44 or 44%. Okay, and then we can check our work and fill all of that in and make sure that it is indeed equal to 1, and it is. So we did a good job. We got it all Gucci and correct. So the frequency, your answer is going to be in percentage because that's exactly what it's asking. So the frequency of homozygous dominant individuals is 46%, and then the frequency of the heterozygous individuals is 44%. Easy peasy, super like clean cut, right? Okay. So the next one says a recessive genetic disorder occurs in 7% of a population of birds, meaning that it's the homozygous, again, recessive genotype. So it's asking what percentage of the population is homozygous for the normal condition. Again, it's asking for population, and it's also asking for homozygous for the normal condition, which means the dominant condition. So again, we put our equations down. We're given the q squared again. It's our 0.07 because it's only 7%. You're just gonna put that in decimals. And then we need to solve for, again, the p squared, which is the homozygous dominant. Okay, so as you can probably guess, we're going to get the square root of that. It's 0.26 for q by itself. P plus q is equal to 1, so we know that p is equal to 0.74 or 74%. If we square that, we get 0.55. And the answer would be 55% of the population is homozygous dominant. Okay. Next one says the population has 1,000 individuals. So you're going to have to do a little bit more math here. It says 123 are homozygous dominant, 455 are heterozygous, and 422 are homozygous recessive. So what are the frequencies of the big B and little b alleles? So the homozygous, or sorry, not the homozygous, the dominant and then the recessive alleles. So it's asking you for, because it's asking just for frequencies, it's asking for just P and Q, what are they? So we're going to write our equations again. And then we're given the uncalculated p squared, 2pq, and q squared things. So all we have to do is divide them by 1,000 because that's what the entire population is. So for example, you would just divide 123 divided by 1,000, and that would be, oh, math is hard, guys. 10.23, something like that. Or 0.123 or 12.3 percent. Sorry. So q squared is, so we're just gonna calculate all of these first. So p squared is 123 divided by 1,000, which is 0.123. And then q squared is 422 divided by 1,000, which is 0.422. And then 2pq, do the same thing. It's 0.455. 0.455. Okay, and then we just need the P and Q, so just the dominant frequency and then the recessive frequency. So P squared is going to be 0.123 from the equation that we just did. We just calculated it really quickly. And again, you're just going to get the square root of that, which is 0.35 or 35%. And then the same thing with the Q. You're just going to get the square root of it, and then you get 0.65. And if you can see that 0.65 and 0.35 equal 1, that's what our equation here is. So checking our work, that adds up. So the answer is that the frequency of the dominant allele is 35% or 0.35, and then the recessive frequency is 65%. Okay. Okay, just quickly, what is the difference between genotype frequencies and allele frequencies in a population? Just think about it, pause this if you need to, and then I will get to the answer. Okay, so genotype frequencies refer to how alleles combine, whereas allele frequencies refer to an allele's relative distribution in that particular population. So how many out of 100, for example, in a population have this particular allele, and that would be the allele frequency. Okay. And Hardy-Weinberg equilibrium is often referred to as a null model of evolution. What does this mean? Think about what we talk about with statistics. What does null mean? So why would it be referred to as the null model of evolution? Think chi-squared, think statistics, and I'll get back to you. Okay, so a null model of evolution is one where no evolution occurs. So there's no difference. Remember when we talked about the null hypothesis? There's no, or it's there's like nothing happening, right? There's no difference. So this is assumed with Hardy-Weinberg if all conditions are met. Okay, so all right, and then the last thing we're talking about is variations in populations. So the more genetic diversity in a population, the better that it can respond to changes in the environment, and more likely to be individuals that can withstand changes. Okay, so species with low genetic diversity are at a risk of decline and/or extinction. I've talked about this a lot in class. The more diverse the population is, the better able it is to survive because the adaptations can be beneficial or not beneficial. It doesn't matter, but the like the ability to select for that beneficial trait will mean their survival, right? Because if there's a very small gene pool and none of those variations and alleles work for that environment, then the population will become extinct. It won't survive. So an example is due to poaching and poisoning, the California condor was reduced to 27 individuals. This drastically lowered their gene pool because there's not as many of them, meaning that there's not very much genetic diversity. And because of this, even through or after restoration efforts, they have lost diversity, and they've increased in numbers, but they've lost their diversity, meaning that they don't have a very good chance of surviving long term because there's no variation. Unless there's like a mutation that happens that really benefits them, they are looking at not a great future for that population. Okay, and that is it. So I will be putting up I think maybe two worksheets for Hardy-Weinberg just for you to practice on your own. If you have any questions, please let me know, and I'll try to make it digital to where you can submit it online, so you won't have to print it out or anything. Well, that's hard because it's Hardy-Weinberg, so it's like equations, but I'll figure it out, and then I will let you guys know via the Google Classroom. Okay, so I will see you when I see you. Stay safe. Make sure that you're making good decisions, and I will. Yeah, I'll see you. Bye.